So I'd like to welcome Ian Glass, a giant of South African astronomy. Very fortunate to have him doing a presentation for us tonight. He started his astronomy in South Africa since 1971, as it says up there on the slide. And he's had a huge amount of awards and achievements from an astronomy point of view. Just quickly, Pierre, is there anything else you'd like to mention?
Sky Guide, the awards, all the posts, we've got all the present, all the awards that can be.
Okay, as Pierre says, if we look in the Sky Guide, it mentions there all the possible awards that there are to get for astronomy. Ian Glass has got. So we're very fortunate to have you giving us a presentation from your knowledge and experience. And we look forward to it. And over to you, Ian.
Okay, thank you. I hope you hear me correctly. So I came here in 1971, as was mentioned, and it was just before the Royal Observatory closed. So this title slide is a picture of some of the different places around South Africa where astronomy is done. I've included Hess, which is actually in Namibia, but it's an important part of the local scene. It does have local participants. And yeah, it's one of the things about astronomy is this, it's quite easy, or used to be easy, for sort of amateurs or people who are not very expert in astronomy to join in somehow. So I just want to mention that a very big change occurred in astronomy from the kind that was done in the old observatories in South Africa in the early part of the 20th century. Suddenly, people like Shapley discovered, for example, that we are living in a galaxy, and he was able to tell us where the center of the galaxy was. He still didn't have a picture of the galaxy. Nobody does, because we can't go far away from it and take a picture looking down on it. But we can infer that it's very like certain other galaxies, like the one I'm showing here. And we live effectively on the outskirts of it. I don't know if you can you see the arrow pointing? We're sort of something a good way out from the center, and we can look towards the Galactic Centre itself. If you look sideways onto a galaxy, if we could, you'd see something like this with the bulge in the middle. This is an infrared picture. That Hubble, of course, also changed our outlook by finding the distances of some of the nearby galaxies outside our own using variable stars. So the old observatory were like this. Excuse me. We had the Royal Observatory Cape, which was funded from the UK, mostly quite old-fashioned with refractors or lens telescopes. So you couldn't do ultraviolet or infrared astronomy with those telescopes. Boyden in Bloemfontein was the international observatory, but it was always very underfunded. And it did actually find a couple of interesting things, but it really was a photographic observatory, quite old-fashioned in its way. The Republic Observatory in Johannesburg, it's still there, but it was South African funded, and it's just one big refractor. And all these observatories concentrated on old-fashioned subjects like compiling star catalogues, observing double stars to get their orbits, getting star distances by parallax measurements, and discovering asteroids and variable stars. So the only advanced area really going on in South Africa was precision photometry, and that was under the control of Dr. Cousins from the Cape Observatory. The Radcliffe Observatory was actually a private UK foundation, again underfinanced. They tended to look for money anywhere they could get it, but as a result of the lack of money, they more or less had to concentrate on traditional problems. But they did do one fantastic thing, and that was doubling the size of the universe by observing variable stars in the Magellanic Clouds just after it was first built in the early 1950s. So that observatory was closed in 1974, and the telescope was bought by SAAO and moved to Sutherland. The other thing that was bad about the astronomical scene in South Africa was the lack of university involvement. But a big change started to happen in the 1970s, and it was caused partly by apartheid and so on, but the UK started to pull out. It wanted to put all its money in the Anglo-Australian telescope, big telescope that was ready for use around about 1974 or thereabouts. It was about 3.8 meters, but it caused a complete change in the whole astronomical scene in South Africa. This is just a fairly obvious map of where all the different things are. The Meerkat, of course, is the most modern of the installations that's functioning. There's more stuff coming along. And then these are the traditional observatories. You probably know all about those. Sutherland was formed, got going at least in 1972, shortly after I got here. So I got here, and it was twiddling my thumbs to some extent, because I couldn't, the 40-inch in Cape Town was being taken apart to send to Sutherland, and the only thing I could get some time on was the Redshift telescope, but that had to be booked quite a few months in advance. Anyway, with the rebirth of astronomy came with the South African decision to fund SAAO, and the UK, as a kind of compensation, offered to pay a third of the running costs for 15 years. I think it started at 10, but it ended up at 15. So Republic Observatory was more or less shut down, and but a very important thing happened in the revival and expansion of the UCT astronomy department, and that added a lot of intellectual power to South African astronomy. And then Hartwell, the radio astronomy observatory, got going in 1975, so that gave another sort of arrow to our bow. And then, of course, more recently, we've had the SKA initiative, which has been very slow getting going, but it is gradually getting going now. And just to tell you, the CSIR was actually in charge of SAAO and the Hartwell Observatory in the early days. Then it became part of the National Research Foundation, and that's in itself is part of the Department of Science, Technology, and Innovation. So we've been treated fairly generously, fortunately. So we've had fairly good supply of funds, not wonderful, but it's kept us going without too many hiccups. So as part of the big changes that were happening in astronomy early in the 20th century, giant telescopes were proliferating. This is where the Americans stole the march on the Europeans by building the 60-inch in Mount Wilson and the 100-inch, and not very long after the 200-inch in Mount Palomar, that came online just after the Second World War. Now, at the same time, radio astronomy was getting going. And in 1933, the first observations were made, but they were ignored by professional astronomers until after World War II, when they began to find out some really interesting things. And of course, the space age changed everything. 1957 with Sputnik. I can remember the excitement at the time. I was just a first-year student, just starting my course. And of course, that led eventually to the Hubble Space Telescope and the James Webb Telescope. But the important thing with radio astronomy was it led to very unusual discoveries, like quasars were very bright quasi-stellar radio sources. Then, of course, pulsars came, all in the 1960s. This was the time when I was doing my PhD, a very exciting time in astronomy. And space vehicles led to the discovery of X-rays and gamma rays. Now, you can't observe those from the surface of the Earth because of the atmosphere, which won't let those sort of rays through. Infrared astronomy developed in the early 1960s. It was delayed by the absence of good detectors until that time. But radio astronomy then started finding molecules in space, and we found the cosmic ray background, and gravitational waves more recently. And of course, technically, CCD images increased sensitivity enormously, because what you could do in the past with a 200-inch telescope, you could now do with a 40-inch telescope. So it was an absolutely dramatic change in sensitivity of equipment, meaning you could look at fainter and fainter things further and further out in the universe. And then, of course, the Hubble Space Telescope overcame the basic problems of atmospheric absorption and seeing, or the shaking of the atmosphere, which were big limitations on conventional astronomy. So this is Sutherland as it existed in the very early days of 1972 to 76. The new sites, we started searching for the new sites very long ago, before I came here. And of course, there were some who favored the Karoo and some who favored further up north. The thing is that, of course, the good weather is spread around the sky about all year round, whereas in the northern parts of the country, the best weather is actually towards the winter, and it isn't much good at all in summer. So Sutherland is about 45% photometric. That means you can do very precise observations about 45% of the time. Certain other things you can do a bit more often, but this is about the limit of what I could handle. Of course, seeing lights from Cape Town and the other big cities, Johannesburg and Pretoria, meant the observatories there didn't do too well. And so the net result was that Sutherland was founded in it opened kind of, I guess we started observing around about June 72 on the small telescope, and it was officially opened in 73. And of course, it's freedom from light and air pollution. That's a good thing of Sutherland. The atmosphere can be very, very steady. It isn't always, but it can be much better than anything you get in Cape Town normally. So, as I said, it was third UK financed for the first so many years. Now, Woolley became the director. He was actually quite old-fashioned in his astronomical ideas, but he really wanted to get things done. He was pretty good at sort of pushing people and making them make up their minds and things. Today, we see so many decisions being kind of put aside and argued over and so on. He just cut right through all that kind of stuff. So the best telescopes were actually moved to Sutherland. So looking at that picture, on the left side is the 74-inch that came in 1976. 20-inch came from Republic Observatory. The one in the middle was actually partly old, partly new. And the one on the right was the 1-meter telescope, or 40-inch, from Cape Town. So in the UCT astronomy department, Brian Warner became the head of department, and he brought with him, he was from Texas, a guy called Ed Nather, who was a brilliant electronic engineer. He knew the Nova computers, mini computers in those days, back to front. And so they built up high-speed photometry. Some of their students made quite significant discoveries. But high-speed photometry led to work on cataclysmic variables, that was things like novas that go off in a dramatic way, white dwarfs and neutron stars. Many of these were starting to get interesting because they were found to emit X-rays. At the same time, they had in the department Tony Farrell, who was very interested in active galaxies. He found a particular galaxy. He made a catalogue, but number 9, Farrell 9, was an ultraluminous galaxy, which turned out to be extremely interesting, very close in nature to quasars, and it'll feature a bit later. So later investigations by the UCT guys showed the existence of a whole cluster of galaxies hidden behind our Milky Way and exerting some gravitational influence on our own galaxy. Unfortunately, we had very good collaboration between UCT and the SAAO. They supplied us with liquid nitrogen and computer power, and we supplied them a telescope time at Sutherland. But so what was happening at SAAO? Well, we had precision photometry going on under Cousins. That's what I mentioned to you. And he was actually retiring about then, but he stayed working till he was about 90, and he actually came up with a very important system of photometry which got to be used worldwide. And though he never traveled much himself, he was very well known internationally. And of course, a lot of new young people, such as myself, came along around about that time. And infrared photometry was my speciality, and it turned out to be a very important part of SAAO in the course of time. So the new detectors, the CCDs, and the first attempt was something called electronographs. They were tried, they worked, but they were very cumbersome to use, and everybody breathed a sigh of relief when the CCDs came along and the electronographs were retired. But we were trying our best to become extremely efficient, and they were much more efficient, say, than photography, which is maybe only 2 to 4% quantum efficient, whereas some of the CCDs these days approach 100%. But our telescopes were small, and so that was why we got hold of the 1.9 meter telescope when Radcliffe decided to close down. And at that stage, there were only two 1.9 meter telescopes in the Southern Hemisphere. We had one of them. And until the Anglo-Australian telescope came along and a couple of the Chilean ones, we still had some of the largest telescopes. So I'm going to talk now mostly about infrared, my own speciality, because before the Second World War, the infrared detectors were very insensitive. It was possible to detect things like the sun and the moon, but not much. You couldn't really detect stars or anything. So as it happened with wartime developments, there was a lot of interest in infrared detection, and so there were a lot of things developed around there, and good detectors and filters that could choose the right bands, because of course you couldn't use glass filters like you did in the optical region. So today infrared has become really quite an important part of astronomy. In fact, the James Webb Space Telescope is almost exclusively infrared, because of course it deals with high redshift objects where the visible spectrum has been shifted into the infrared. But the infrared is technically very complicated compared to what astronomers were used to, at least. And the people with technical competence usually didn't know much astronomy. So I was sort of in a fairly good position that I was a physicist by background, and I knew a lot about astronomy, although I really hadn't studied astronomy as a main subject. But I had worked in space studies of various kinds, in X-ray astronomy, and in optical interferometry. This is to give you a sort of clue of a sort of feeling for the infrared. The picture on the left is actually from a paper by William Herschel, who discovered infrared radiation in the year 1800. He did that by casting a spectrum on a table like this and measuring each color in turn using a set of thermometers. I won't go into the full details, but he obviously found that most of the heat was coming out in the red part of the spectrum. And that's shown on the right side, which is a diagram of the amount of heat that you see against the colors of the spectrum. So when I just before coming here in 1970-71, I'd learned infrared techniques at the California Institute of Technology, where I was working at the time. And then I was recruited from there to work at the Royal Greenwich Observatory in England. So while there, I built my first infrared photometer. That's why they wanted me. But to use it effectively, I had to work somewhere where the skies were reasonably clear. So I sort of asked for and was sent as a visitor to the Royal Observatory Cape for 3 years, because we knew that the conditions out here were often quite photometric. I mean, somebody like Herschel, William Herschel used to say if he got 10 really good days a year, he was happy. And that's working from Slough in England. So in the infrared, we have to know there are some basic properties. In infrared, all objects radiate according to the temperature. And normally in infrared, we use absolute temperatures starting at 0 Kelvin, which is same as minus 273 degrees Kelvin. You cannot get colder than that. Minus 273 degrees centigrade. You can't get colder than that. So we measure from there. So room temperature works out to be something like 300 degrees absolute. And that's you and me and everything around us just about. So the peak wavelengths in microns, which is what we measure with for the sun, which is 5,800 degrees, comes out to be about half a micron. And that's the same as, that's basically visible light obviously our eyes are built to make use of sunlight. So it's equivalent to 5,000 angstroms or 500 nanometers in other terms. But the infrared astronomers mostly think in microns. The room temperature objects that are radiating, its maximum is about 10 microns. So you and I and everybody else and everything is radiating about 10 microns. So that makes it quite difficult to make celestial objects, to observe celestial things if you've got this huge background. Even the telescope is radiating itself. And the most extreme sort of infrared sources are interstellar dust, for example, which might be just radiating a few degrees of absolute zero. And so they are best observed from space. The top picture here, well, the middle picture I should start with, that is actually the Milky Way looked at in visible light. It's about the central 2 or 3 degrees of the Milky Way. And you see it's covered with black clouds. That's because there's a lot of dust and gas on the way. Now, the top picture shows the same thing in fairly long wavelength infrared. And there it's not bothered at all by absorption. That's one of the advantages of infrared, that it passes fairly freely through gas and dust. Only the most extraordinarily dense regions stop it. And the bottom picture is a gamma ray picture. I won't go into that now. So this is just, as I mentioned, everything is radiating. So it's sort of like doing photometry in the daytime using a fluorescent telescope. You probably know that if you look with a big telescope and you can point it at a star, you can actually see a star in the daytime. But of course, you're looking at it against a bright sky background, but you can actually pick it out if you have a powerful enough telescope. And the problem is to point the telescope in the first place. So glass lenses, like our old-fashioned telescopes, are limited to visible wavelengths, actually. And so this graph at the bottom shows how the Earth's atmosphere lets through infrared light. So you see on the left side of it is actually, it's clear because it's visible light coming through. That's just that very tiny part on the very left. And then there are some bands that let through different parts of the spectrum. So the main thing, there are certain infrared bands that we concentrate on, and we use these interference filters to actually select the band we're interested in. Then you see from 5 to 8 microns, nothing gets through. And it's all due to molecules in the atmosphere like water and carbon dioxide and what else? Anyway, so around about 10 microns, there's a very wide band. And that's one of the few regions where we can observe from the ground. But once you get out past about 15 microns, there is actually a bit more, around about 20 microns, but after that, it's completely opaque until you get into the radio region, which starts at 1 millimeter, which is 1,000 microns. So that's where satellites come into their own, because they can get above all this. So just to tell you a bit about the technology, infrared photodiodes, they are the detectors. They are solid-state diodes, and they're made of exotic materials. Instead of being silicon, like most electronic stuff, they're made of indium antimonide and some other elements as well. So optical materials, you can't use glass, but you can use calcium fluoride, that's fluorite. And you can use sapphire. Sounds exotic, but it's not all that expensive. It's aluminium oxide and potassium bromide. The trouble is some materials are deliquescent. That means that if you expose them to water vapor in the air, they deteriorate very rapidly. As I mentioned, interference filters are very important to find your wavelengths. And the optical design can be complicated because it can be very miniaturized. And then the cryogenic design, that means because you have to house the detectors in cold vessels, you have to worry about what happens with expansion and contraction and whether refractive index of glasses and crystals change as you go to very cold temperatures. And then many of the detectors are low noise devices. They're not like photomultipliers, which put out a fairly substantial signal. And of course, you're working with cryogenic liquids. Helium is a very awkward thing to work with, and liquid nitrogen or solid nitrogen sometimes. And everything, it depends on vacuum technology. You basically house things in things like thermos flasks to keep everything cold. And of course, nowadays, every instrument, just about of every kind, involves computer data processing. This was my infrared lab as it looked in the 70s. It isn't very different now, but you see those big vessels contain the liquids, the liquid gases, liquid helium and liquid nitrogen. Liquid nitrogen costs about the same as beer. Liquid helium costs about the same as whiskey. So you have to conserve it very carefully. And of course, it's boiling off all the time. So if you have 30 liters of liquid helium in that big container, after a month, you have nothing left. So you have to buy the stuff and use it before it evaporates. And in the early days, it was very tricky because only Wits University could produce liquid helium. But nowadays, of course, we have all these magnetic resonance scanners, tomography for medicine. So the result is liquid helium is much more freely obtainable, but it's not cheap. But at least it's accessible. So those are just some of the instruments we had to use in those days. And these are some of the things I designed. So on the left is a diagram of my photometer. And on the very left of that is the cryostat, you see. And that's what contains the detector and the filters and everything else, because you basically want your detector to be surrounded by cold things so that room temperature doesn't interfere with their operations, with the radiation from room temperature objects. And because of the fact that the sky is so bright, you normally compare a little piece with a star in it to a little piece that doesn't have a star in it. So you do what's called sky chopping. So 12.5 times a second, you switch from looking at the star to looking at the star plus sky. And so you basically insert the difference, the actual star signal. So it's a technique that's used a lot in radio astronomy. And on the right, you see the first equipment that I used. This was the stuff, this was in Sutherland on the 40-inch, probably just when it first came into use again after the move to Sutherland. And you see the photometer there. Again, this time the dewar is on the right, but you have to set the telescope optically using your eyes to find the object. And then you have a guider, that's like you have when you're taking long-term photographs, you have to guide the telescope. And those are some pictures of the equipment. Left side shows what goes on inside the cryostat. This part is all cooled to something like 63 degrees, absolute, with solid nitrogen. And you see there in the middle is the detector, but there are filter wheels and aperture wheels to choose which part of the sky you're looking at. And there's a cold amplifier to get very low noise performance. So it's quite technically interesting. In the middle is another kind of chopper. This was used on the 74-inch. And instead of having those rotating mirrors like I showed you in the previous thing, this mirror is a secondary mirror that actually vibrates slightly, and it chops from star to sky, again at 12.5 times a second. And on the right is another cryostat. This was used to make 3 colors maps of parts of the sky. We'll see more of that. So the 74-inch, when it came, it's a very old-fashioned telescope, but we did a lot of work on it to make it more efficient. At the very top of it, you see a very tiny secondary mirror. That's actually the small infrared secondary. and it's designed so that when the detector looks up the tube, it doesn't see anything other than cold sky and the object that you're interested in. So it's a much more efficient way of doing infrared than using one of those rotating shoppers. We also made the telescope to point more accurately and generally be easier to control. And also we arranged so that we looked at, instead of having to look through it to center the object, we had integrating television and so on that gave you high sensitivity view of the part of sky you were looking at. And of course, nowadays, in that time, it was still tubes. We had these special Vidicon cameras that were very hard to get hold of because of sanctions. But eventually, we switched over to CCDs, and nowadays, all the finding cameras are CCD cameras. And this was one of our great efforts. We made actually the best picture of the center of the galaxy. It's about 1 degree by 2 degrees, and it's made in 3 colors. So the red is actually what you see at 2 microns. So that's the center of the galaxy peeping through the dust clouds. You see there are still some black spots here and there because some areas just have fantastically dense dust clouds, and even the infrared can't get through them. So we made essentially the best picture of the Galactic Centre that was available for a few years until array detectors started coming. Because for a long time, there was no equivalent of CCDs for the infrared. You had to work with single element detectors and just scan the sky. And one of our infrared, earlier when we started getting array detectors, this was a very crude one that we got from Japan. It was quite a large format one, but very, very insensitive. The efficiency was only about 2%, whereas modern ones, of course, get up to 12, nearly as good as CCDs. And here you see a Japanese astronomer that worked at the observatory, Kaz Sekiguchi. He was observing, and he's filling up, he's got a liquid nitrogen in that flask, and he's going to fill the dewar with this white styrofoam thing. Unfortunately, the pointer doesn't show. I don't think so. Yeah. But he can pour nitrogen in, and that cools down the cryostat, which is the gold-colored thing there. And of course, on the right, near where you see the hand paddle, is a black box, and that's the autoguider. So that's a typical Santa Barbara autoguider. It's not very expensive, so probably quite some of the amateurs would have those as well. But the important thing that was done with that camera was these photographs of the collision of comet Schumacher-Levy with Jupiter in 1994. And this actually caused quite a sensation internationally because we were the first people that realized that the way to do this was in the infrared. If you tried to do it in visible light, you didn't see very much. But from the top to the bottom, you see the comet crash gradually brightening up. It's right at the bottom of the picture in each case, and then it fades away again. So this was one of many. There were many pieces of the comet Schumacher-Levy that bumped into Jupiter. This was just one of quite a few. But in the pictures, you can see the moon Io on the right, and as you see from the top to the bottom, Io is going a little bit further away. Just as you can see the red spot is slowly going to the left as the planet rotates. So this was one of the very successful things we did in the infrared in those days. So what other things do we do at SAAO? Well, I mentioned to you, distance is a very, very important thing. So the basic way of getting a distance is with trigonometric parallax. So you treat the Earth's orbit as a baseline, and you take pictures in summer and winter, and so you get quite a long baseline, and you can see the nearer objects seem to move compared to the objects on the other in the distance. So that way you can actually work out the distance of the nearest stars, but you can't do an awful lot of them from the ground. They're just so far away and the angles are so small that we can detect very few that way. So that's where Gaia and Hipparchus have revolutionized things, because with those satellites, they're right above the Earth's atmosphere. You don't have to worry about the instability of the atmosphere, so they can do extremely accurate parallaxes. But even so, they can only get a certain distance towards the center of our galaxy before they find it, the angles are too small. So I mean, it's like trying to measure something the size of a man on the moon. It's really extraordinarily small angles. But the next important thing is having variable stars, such as Cepheids, Lyrae, and Miras, which have period luminosity relations. And so if you can measure those, then you can tell how far away objects are, because if you find out the average brightness, apparent brightness of a source and its period, so anyway, even if you do see Cepheids and Lyrae, you have to know how to calibrate them as bright as standard sources. And that means you have to use stars where you already know the parallax for some reason. So you go from the nearest stars to much further ones that way. And then when you run out of steam, so to speak, using variable stars, you go to supernovas. Now, supernovas at their brightest actually have a standard brightness. But you don't have them available all the time. You have to take the opportunities when they come up, and that way you can get the distances. You can get the distances of very distant galaxies. Okay, so this was some of the work. The most famous things I did personally were to find the period luminosity relationship for Mira variables. Now, Mira variables are very conspicuous variables, but the trouble is, in the visible, they do not make a nice period luminosity relation. And that's because they're extremely cool and their spectra are eaten into by bands of cool gases. But if you examine them in the infrared, where you have a much better idea of their true luminosity, you find they do obey a nice period luminosity relation. So, for example, from about 100 days, that's log p of 2, to about log p of 3, which is 1,000 days, then they form quite a nice linear relation. So this made Mira variables useful for finding out distances. And Tom Lloyd Evans had found some Miras in the Large Magellan Cloud, and he told me where they were, which was a sort of a professional secret almost. And so I was able to measure them. And so it's from that we found this nice relationship. And it turned out to be quite an important theme, because some of the other people at the observatory, like Patricia Whitelock and Feast himself, did a lot of work on distances using Mira variables. The other thing I did, and I just mentioned two of my most important things, and that was to study quasars and active galaxies. Now, on the right, you see this sort of imagined picture you don't see this detail, but this is what people think they look like. So in the center, you have a very bright source in ultraviolet light. And all around the outside, you have this red dusty area, which is much cooler. And if you measure these things with photometers, infrared or visible photometers, the visible and UV turns out to be varying quite quickly, because you're looking directly at the center of the quasar see for a galaxy. But what you find is that the dust radiation from the outside takes some time before it responds to what's happening. So the ultraviolet light from the center warms up the dust, and the dust responds that way. When the ultraviolet gets brighter, the dust gets brighter. But there's a delay and in the case of Ferrol 9, it's about 400 days, because that's how long it takes for the ultraviolet light from the center to get out to the dust. In other words, the whole thing measures several hundred light days across. So we were able to confirm that this was actually a valid model. So to carry on a little bit, the Japanese telescope was built around about 2000. I also helped quite a lot with the logistics of getting that done. It's a survey telescope, and of course by then the types of detectors available had greatly improved, and we had 3 separate 1000 by 1000 element infrared arrays in a camera on this telescope. So it was mainly used for doing surveys of the Magellan Clouds and the center of our own galaxy. But this telescope is actually technologically probably the most sophisticated one on the mountain at Sutherland. It's extremely precise pointing, and it was made mainly by Nagoya University, but the basic telescope was made by a Japanese company called Nishimura. But they used a lot of student labor to do the programming and small part design. So Sutherland today has about 20 telescopes, different various types and sizes. SALT, which actually isn't in this particular picture, is the largest single dish telescope in the Southern Hemisphere. It's one that I don't use for infrared. It's not particularly suitable for infrared, unfortunately. But the 1.9 meter Radcliffe telescope is very much in use still, even though it's fundamentally nearly 90 years old. It's in that dome shaped like a tin can. And recently there was built the 1.8 meter prime infrared telescope. It's another Japanese project. I'll tell you more about it just now. Then there's the survey telescope I just mentioned. Then there are some 1 meter telescopes, and a telescope called Mirlect that automatically watches what the Meerkat telescope is doing, the radio telescope. So while it's observing the radio, this is taking optical pictures of the same area of the sky. And of course, there are various automatic telescopes there. It's quite popular now to run telescopes by remote control, so people don't always have to go to Sutherland to do their observations. And these automatic telescopes are from various different countries around the world, even including Russia, Korea, Germany, Poland, UK, and USA. And there are some other non-astronomical things there, such as things for monitoring the gravitational field of the Earth and looking for evidence for atomic explosions and things, and airglow monitors. So it's quite a sort of scientific metropolis up there. So the SALT telescope, that's what it is, cutaway diagram of it. It was chosen to give the maximum collecting area for the minimum cost. And it's made up of the main mirror is made up of lots of little mirrors, about a meter across, 91 of these hexagonal mirrors, all placed side by side, but they have to be aligned very carefully with respect to one another to give a perfect image. So the light is reflected to a spherical aberration corrector at the top in front of each instrument. So the way this works, the main structure remains stationary, and only the tracking beam at the very top of the telescope is moved during an observation. So it was constructed starting in the year 2000, and that's the year officially I actually had to retire, but the construction took about 5 years, and there was quite a lot of problems in the beginning. So it took several years to sort them out, but I believe it works quite well now. And it's operated, it's not owned wholly by SAAO, by South Africa. It's partly owned by various foreign partners. So I think South Africa has about a third of the observing time. It may have increased since, but I'm not sure. So the most recent big telescope is this PRIME. It's a very interesting infrared telescope. It's from another Japanese university, Osaka, and from NASA, the University of Maryland, and the Astronomy Center of Japan. It's called the Prime Focus Infrared Microlensing Experiment. So the idea is to monitor zillions of stars in places like the Galactic Centre. It uses infrared because, of course, the infrared can pass through the gas and dust that's in the way. But by looking for anomalous spikes and things in the light curves of each individual star, and you can do this thanks to the power of computers these days, then you can pick out signatures caused by Earth-sized planets doing microlensing of stars in the background. So this way you can find out a lot about low mass stars in areas like the Galactic Centre. But one of the interesting things about this telescope is that it has a very large format infrared detector, one of the largest in the world. And they were very fortunate to get NASA in as a partner, because that gave us access to these very large infrared arrays. So 67 megapixels. If you think, you know, a fancy ordinary hand camera has nothing like as many pixels as that. So other themes, I mentioned distance scales. Occultations are very important. And historically, of course, Joe Chernes was one of the co-discoverers of the rings around the planet Uranus in 1977. And planetary rings have become quite an important sub theme for astronomy. But he actually did this observing from Cape Town, because as it happened, Sutherland was clouded out on the day involved. And then a lot of variable stars of different categories, you know, are well worth understanding, either with high-speed photometry or just over long-term for distance measurement purposes and so on. So now to just get down to some of the statistics, the number of staff figures in SAAO is now 182. You can see people with more or less science activities, 61, technical, 31. IT is very important these days, 16. Then other types of support like mechanical and even just plain cleaners and people, down to quite a few of those. And outreach has become very important, education and teaching. So every year, the sort of refereed publications is quite high, around 230, but that includes visitors, staff, and many collaborations. So there are very few papers published as individuals. You know, most people do it in large collaborations. So I mentioned the rest. Oh, I did. Yeah, when the Royal Observatory ended, there were only 38 people employed there. This is one of the many themes that the SALT telescope has been used to investigate. This has been an international project, of course. Once the counterpart of a gravitational wave source was found, there was a great deal of interest in finding out what it was. So you see pictures sort of before and after here. The little, it indicated which is the star where it all came from. So the total number of astronomy researchers in the country as of this year, Fernando Camilo counted 293 unique names. So, and there were something like, how many institutions? 17 institutions involved. So you see, most of the universities are now involved, and as well as that, the Space Agency and Institute for Data Intensive Astronomy, which is a kind of computing outfit. And it also includes people in University of Namibia, which is gradually picking up in terms of doing astronomy. So how has the field grown in South Africa? In the early 19th century, there might have been 3 people doing it. By the early 20th century, there were 12 people at the end of the Gill regime, say. And by the middle of the century, there were about 30. So now there are about 300 PhDs in astronomy and related sciences. So whether they can all eventually find jobs is another issue. The number of amateur astronomers in South Africa is about 1,000. Some of them do very good work. You probably all know about Clyde Spot, for example. And so worldwide, according to the IAU, there are about 13,000 astronomers, of which nearly half are in America, 1,000 in the UK, and about 25,000 papers are published each year. So, well, we'll have a few minutes mentioning of radio astronomy. It started at Rhodes University 50 years ago, and of course, Hartebeest Hook came online 75. And now, of course, we have the Carnarvon radio observatories starting around about 2013. So I'll just mention 2 important wavelengths: atomic hydrogen, and that's in, if it's not redshift, it's 21 centimeters, and OH radicals. It's the first molecular type thing to be discovered. It's 18 centimeters. And so SAAO, which is now the equivalent of SAAO, but for radio astronomy, it incorporates Hartrau, the original observatory up north near Hartebeest Dam, and the observatories at Carnarvon. So Carnarvon is chosen because of the low population density, radio quietness, and the people there are not allowed to use cell phones, which doesn't please them at all, but it's also part of the NRF structure. So this is the Hartrau telescope. It started off as a deep space tracking station, and it was used quite a lot for the Mariner program. And so, for example, the Mars images and things came through that telescope. But eventually NASA pulled out, it didn't need it anymore, and it became a radio observatory in 1975. So it had to be re-equipped with radio astronomy type receivers and so on. But it's a very versatile telescope, covers a large range of wavelengths, and it's used for monitoring variable sources, and it's used as part of a worldwide network for finding out various very accurate angular sizes of distant objects. So that at Carnarvon we have these. So you have the cat, which is more or less now obsolete. Meerkat, which is the one that's really going great guns at the moment, 64 dishes. And the SKA is going to add another 133 dishes to have a total of around 197 eventually, I think it is. So 10 of these are complete as of now. I think they have tried out some of them, but they're not really hooked up to the network yet. And then there are projects called PAPER and HERA, which have to do with studying very distant hydrogen radiation to try and get some feeling for the early days of the universe, when it was just possible to see the earliest formations that were not hidden by extreme temperatures. And then the IRAS, which is just a planned thing, and the CBAS, it's a single dish survey telescope for hydrogen. I'm not sure if it's still running, but I think it is. So the angular resolution of a radio telescope depends on its diameter, in fact, any telescope. But by having lots of spot, instead of one big continuous dish, a couple of kilometers in diameter, you can use a lot of little dishes coupling together with computer technology. And that way you can obtain high detail that you would get from a single big dish. That's the sea bass, and the last picture that Jonas sent me. It's not quite in the same place as the rest of the telescopes at Carnarvon, but nearby. And of course, it's quite a job to get together all the data from all the different telescopes in Meerkat. So they are, all the signals are fed to the what's called the Karoo array processor building, and then they have a lot of backup power and things like that. And this whole complex is hidden behind a kind of artificial mountain to prevent radio interference coming from the computers and interfering with the antennas. So everything is fed by fiber optics, and it takes quite a supercomputer to put everything together. So this is the Karoo Array telescope, the original CAT, as it's called. It's actually now mothballed. It was a kind of experimental precursor telescope, try and find out what problems you might have operating something an array of this kind in Carnarvon. And it was used for certain things like variable sources and black hole candidates and so on. In the current Meerkat array, that's with 64 antennas, 13.5 meters diameter each. That's very much a functional telescope, and it's what's called a Gregorian feed. So the main parabolic dish feeds another a concave dish, and the receivers are just in front of it. There are 3 receivers on each telescope. And this is a flyover of the site. Gives you some idea. So the most distant telescopes are out a few kilometers from the center. But by having distant telescopes, you get fine detail. By having close together telescopes, you get coarse detail. That's the way it works with radio astronomy. And those are the sort of statistics of it. 64 antennas, each 13.5 meters diameter, 42 tons each. And they are intended to work over quite a large wavelength region. I don't think all of it's functioning yet, but they do work. The middle band, 18 to 30 centimeters, obviously works. But you see the fantastic amount of data. It's something like 3,400 million samples per second. And that for each antenna of the 64. So that has to be boiled down. You cannot send that quantity of information practically down to Cape Town. So as much as possible is actually processed on site. And this is the famous picture that at 23 centimeters wavelength. So what you're looking at here is the center of the galaxy, and the radiation mechanism is not stars particularly. It's synchrotron radiation. It's caused by electrons spiraling in magnetic fields. So most of it's that, especially those spicules, as they're called, the sort of narrow features. But on the left, those 3 big things are supernova remnants, probably, and they typically have quite a lot of high energy particles spiraling in magnetic fields, which is what causes them to be bright in radio waves. And this is just another picture of the same thing, but it's much deeper, and you see these sort of big loop structures above and below the plane of the galaxy. And they are quite interesting discovery, I think, purely due to Meerkat. So they think there was some sort of energetic event several million years ago that was probably something to do with the black hole in the Galactic Centre, which is right in that bright part. And again, it's radio continuum radiation from synchrotron radiation. Oops. And this is just to show you, on the left, it's a normal picture of Fornax A, NGC 1316, which is a very bright, well, about the brightest elliptical galaxy, and it's also a bright radio galaxy. But Meerkat has been showing up these things shown as green, which are sort of hydrogen clouds associated with the galaxy. And it's been looking at very, very deep images. This is a 130 hours exposure. And it sees lots of very, very distant galaxies that are responsible for a lot of the star formation in the universe. So this is the first radio telescope sensitive enough to make a detection of this kind. Okay, what's going to happen further? Originally, SKA was conceived as being a square kilometer array, as having a whole square kilometer of collecting area. Now it's an international organization funded by intergovernmental treaty, and it has quite a few members. And it has two sites. You probably all read about the arguments between South Africa and Australia as to who was going to get it. I think a lot of the most interesting part is actually in South Africa, but the low frequency part is in Western Australia. So it's been very slow to get moving, but it seems to be getting on fairly well now. And they say full completion about the year 2030. So the mid is the name of the part that's in Carnarvon. And as you see, there are 133 15-meter antennas under construction, of which 10 have been made so far as I know. And it's combined with 64 existing 13.5-meter telescopes. So Meerkat was, I think, wholly South African financed. I think it cost about 4 billion rands. So it's quite a chunk. And yeah, so that gives you the wavelength range and type of telescope. Paper, I won't go into this, but I'll just quickly show you some of the installations at Sutherland. These are for looking at early stages of hydrogen formation in the galaxy. So we're talking about things near the current observed maximum redshift, which is something like 11, I think. I'm not sure if that's the latest, but it's in what they call the era of reionization. So you cannot see things earlier than that because radio signals are blocked by the heavily ionized atoms at that far back in time. And this is the paper, which is a similar type of thing. There are actually three, and this is a planned one, but I don't think it's got very far so far. So just almost to finish off, I'll mention that in Namibia, they have the HESS telescope for picking out gamma rays. And this has been a fantastic experiment because gamma rays are high energy cosmic rays, but they have the advantage that because they are not charged, they come straight to us from wherever they started. Whereas if you have charged cosmic rays, they get deflected by the magnetic fields of the universe, whether it's in the galaxy or intergalactic ones. So this has been able to pick up high energy gamma rays. It's a very sophisticated thing electronically with very high speed timing involved and everything, because everything is over in a few nanoseconds. So as soon as they pick up a signal, they have to take a picture of it, and they can find out what direction the gamma ray came from. So they basically formed with violent events like supernovas, and they also probably involve magnetic fields where they're at their origin. So they make, when they come into the Earth's atmosphere, they make a kind of a shower of secondary particles like electrons and gamma rays. And this little picture on the right shows you what one of those antennas photographs. So it sees something like a lozenge-shaped little cloud of light emitted by these very high-speed gamma rays and electrons. by the electrons actually, and it's called Cherenkov light. It's actually a kind of a shock wave because you know, even though light travels at speed c, when it's in air, then basically it does get slowed down, and these high-speed particles coming in cause a kind of shock wave, and that's what gets picked up, this Cherenkov light. It's actually blue light, although in this picture it's shown as red. So this happens to be, I think this is the last picture I'm going to show. It's actually a unique picture, but gamma ray bursters were originally picked up by satellite detectors, and they are, of course, they're high energy gamma rays, and they're short-lived. And using the HESS, they were able to actually take a picture of one of these bursters. Now, it so happens that HESS is now being superseded by two bigger arrays, one in the Northern Hemisphere around the Canary Islands, and the other in Southern Hemisphere in Chile. So unfortunately, our HESS in Namibia probably only has another couple of years to go before it gets superseded. So I think that's the end of my talk, but I'm happy to answer questions. Maybe you can relay them by means of cell phone, if there are any. Oh, well, Miras are very bright stars. Mira itself, it's called Mira Ceti. It's one of the first variable stars ever discovered, but they vary a lot from very, very great brightness to very faint brightness by maybe sort of 5 or 6 magnitudes between the faint and the bright state. And yeah, they have long periods. They are from about 100 to 1,000 days in period. So they're actually very easy to pick out in another galaxy. So they're quite important to be able to use them as distance indicators. Yeah, they actually make quite an effort. We have a lot of school visits and people going out to schools and giving talks. And yeah, I mean, there's a whole outreach department whose job is mainly to publicize astronomy. This was something that didn't exist when I first joined. You know, we had our 2 open nights a month, and that was it. But nowadays it's considered, you know, actually an important part of astronomers' work to spread the word.